In this video, I will talk about the HEMT structure, HEMT, High Electron Mobility Transistor. My dear friend, stay tuned with my channel. In future, I will publish more videos. I need your support and love so that I can continue my services with you. Please share my channel as much as you can. Please join my Telegram group for more details. So let's start. In this video, I will talk about aluminum gallium nitride high electron mobility transistor. A high electron mobility transistor is an heterostructure device composed of two different layers in which the wide bandgap material is grown over the narrow bandgap material. In the next slides, I will discuss about the material properties of gallium nitride versus silicon, spontaneous and piezoelectric polarization effects, HEMT operation theory, in which I will tell you how to find out the drain current of HEMT structure, aluminum gallium nitride HEMT device structure. I will discuss in the next slides. Gallium nitride based HEMT for high voltage operation. Gallium nitride based high electron mobility transistor is used for high voltage, high power switching and regulating for space applications. The gallium nitride materials has high bandgap energy, 3.4 electron volt of gallium nitride and 6.2 electron volt of aluminum nitride, and it has high electrical breakdown strength, which can translate into high transistor operating voltage and high breakdown voltages of gallium nitride devices. The high saturation velocity causes the high output power delivered from small size gallium nitride devices, which makes the gallium nitride technology more compatible with high power applications. Gallium nitride based high electron mobility transistor, and in particular aluminum gallium nitride devices, have become one of the most promising solid state microwave power devices due to their ability to produce high power density at higher frequency as compared to silicon and gallium arsenide based device. The main point is that the gallium nitride devices is used for high voltage application because it has high bandgap energy, 3.4 electron volt of gallium nitride and 6.2 electron volt of aluminum nitride. And one more thing, because of the high saturation velocity, gallium nitride and aluminum nitride high output power delivered from small size gallium nitride device, which makes the gallium nitride technology more compatible for high power applications. Next is the material properties of gallium nitride versus silicon. Gallium nitride based devices have the following potential benefits as compared to silicon. Earlier, nowadays we are using the silicon material, but in the future gallium nitride will replace this silicon material. The properties of gallium nitride make it one of the most attractive materials for power electronic application when compared directly to the silicon, for example, which has been the dominant force in the electronic field for almost 40 years. It becomes clear why it attracts so much attention. These properties include large relative band gap, 3.4 electron volt compared to 1.1 electron volt of silicon. High critical field, around 300 volt per micrometer compared to 30 volt per micrometer in case of silicon. High electron mobility and the saturation velocity. It is about 700 to 2000 centimeter square per volt second and 2.5 into 10 raised to power 7 centimeter per second compared to 1350 1350 centimeter square per volt second and 1.0 into 10 raised to power 7 centimeter per second for silicon. So that the gallium nitride has high relative band gap, 3.4 electron volt as compared to 1.1 electron volt in case of silicon, and it has also high electron mobility, 700 to 2000 centimeter per square per volt second in compared with the silicon has 1350 centimeter square per volt second, and the saturation velocity is also high. Saturation velocity of gallium nitride is about 2.5 into 10 raised to power 7 centimeter per second in comparison with the silicon has 1 into 10 raised to power 7 centimeter per second. Higher breakdown voltage of gallium nitride has lots of advantages. The critical field of gallium nitride is around 300 volt per micrometer, meaning that the electron on gallium nitride with a spacing of 1 micrometer. 300 volt per micrometer means that it has the spacing of 1 micrometer. Aluminum gallium nitride and the gallium nitride high electron mobility transistor display own resistance less than 1 milliohm centimeter square compared to silicon has very high own resistance. It is about 100 milliohm centimeter square. This is one of the advantages of silicon over gallium nitride. The silicon material leading to much lower on-state power loss. This will improve the efficiency of the device in switching application, for instance. Another is the advantages of gallium nitride over silicon. Faster switching frequencies resulting in circuit using gallium nitride HEMT requiring smaller capacitor and inductor so that it will reduce the overall cost and size of the device. Higher temperature capabilities. Gallium nitride devices have been shown to work beyond 300 degrees C, leading to much reduced need for large heat sink and cooling system, so that the overall cost of the device gets reduced. Another is most important effects in HEMT device, that is spontaneous and piezoelectric polarization effect. The crystal structure of gallium nitride is hexagonal, where the bilayers consist of two closely spaced hexagonal layers, one formed by the gallium atom and other formed by the nitrogen atom. The lack of inversion symmetry with the strong ionicity of the covalent bond leads to the polarization vector, and these polarization vectors are adding along the covalent C direction, resulting in a macroscopic polarization. This polarization effect is referred to as a spontaneous polarization, and it is represented by PSP since it occurs without any external field. You can notice down in the figure that this is the gallium structure and this is the nitride structure, and this is the aluminum gallium nitride structure. You can see in the energy band diagram. When a thin aluminum gallium nitride layer is grown on the gallium nitride buffer layer, both layers experience strain caused by the lattice mismatch. This strain is an well-known approach that is called piezoelectric polarization. It is represented by PPE. By increasing the known ideality of the crystal lattice, the piezoelectric polarization effect is continuous increasing. From the first diagram, increasing the aluminum content in the strained aluminum gallium nitride leads to an increase in the piezoelectric polarization. By increasing the aluminum content of the aluminum gallium nitride layer, the overall polarization is equal to the spontaneous polarization plus piezoelectric polarization. This is the crystal structure of a gallium nitride or aluminum nitride. And the second one is the polarization induced sheet charge and direction, and this is polarization induced sheet charge and the direction of the spontaneous and the piezoelectric polarization in the gallium phase strained aluminum gallium nitride heterostructure. 2DEG is the two directional electron gains density. The two-dimensional electron gains density achieved in the gallium nitride HEMT device is well above the 10 raised to power 13 centimeter square without the requirement of any international doping in the device. The presence of the spontaneous and the piezoelectric polarization charges are responsible for such high value of two-dimensional electron gains sheet carrier density. Furthermore, the increase in aluminum mole fraction in the aluminum gallium nitride material will deepen the quantum well and hence facilitate more electrons to be confined in the channel. Therefore, the polarization charge density and band gap discontinuity can be controlled using the aluminum mole fraction. This offers the flexibility of optimizing the HEMT device characteristics. 2 points to be noted. If we are increasing the aluminum mole fraction in the aluminum gallium nitride, it will increase the piezoelectric polarization in the device. And the second thing, if you are increasing the aluminum mole fraction, it will deepen the quantum well and hence facilitate more electrons to be confined in the channel. One of the advantages of introducing aluminum in the aluminum gallium nitride layer, it can reduce the discontinuity problem in the band gap structure. Next is the HEMT operational theory. The current flowing between the drain and the source contact can be written as follows: rate at which the charge moves across the gate from drain to source. ID is equal to Q NS V effective WG, where V effective is the effective velocity of the electron in the channel. NS is the charge density and WG is the gate width. The sheet carrier density can vary from a maximum value NS naught to a minimum value of 0 depending on the gate wise, assuming that the value of NS is in between the 0 and NS naught, and the NS is given by, this is the formula, please note down, in which D aluminum gallium nitride is the thickness of the aluminum gallium nitride Schottky barrier layer. Delta D is the effective distance between the 2D EG and the heterostructure interface. VG is the gate wise. So when the gate wise is equal to the threshold voltage, there will be no current can flow between the drain and the source, so that NS is 0 and the corresponding value ID is also 0. In this video, I have designed a simple structure of current voltage characteristics of aluminum gallium nitride HEMT structure. The proposed model accounts the polarization charge density in estimating the 2D EG sheet carrier density. 2D EG is the two-directional electron GaN density. The influence of aluminum mole fraction and aluminum gallium nitride barrier thickness in determining the pinch-off voltage variation and current characteristics is discussed in details. The effect of source and drain parasitic resistance have also been incorporated to accurately predict the extrinsic HEMT characteristics. This example demonstrates ID versus VDS and ID versus VGS calculation in an aluminum gallium nitride HEMT device. This example demonstrates construction of the heterojunction structure using FS index. Second one, material and model parameter specification. Third one, simulation of ID versus VDS and ID versus VGS characteristics. Fourth one, polarization commands enables the automatic calculation of added interface charges due to spontaneous and piezoelectric polarization. By introducing the polarization command, you will get both spontaneous and piezoelectric polarization. PSP and PPE specify the spontaneous polarization and piezoelectric polarization respectively. Display of the results in Tony plot. The device under consideration is a simple aluminum gallium nitride HEMT structure. The main concept here is that the polarization charge is calculated using the built-in model as specified by the polarization parameter on the model statement. After the initial solution is obtained, the gate voltage is ramped to minus 10 volt. Then the ID versus VG curve is extracted using VGS voltage minus 10 to 1 volt. I will explain about in detail in the code. A family of drain characteristics are then simulated with or without lattice heating taken into account by ramping the drain voltage from 0 to 15 volt at various gate voltage. Finally, the family of curve is plotted using the Tony plot. I will discuss about these results of Tony plot in detail in the code. So let's go to the code. The progress of aluminum gallium nitride HEMT has been quite impressive over the years, and nowadays it is widely used in practical application. Therefore, an accurate model of the device is highly desirable. So let's start with the same command go atlas. After that, I have set the parameter V start is 0 and V stop is 15 volt and the V increment is 0.5 volt. Meshing width, I have defined 100. X meshing is start from the 0 to 900 nanometer with different spacing. Initially the spacing starts from the 0.25. After that 0.25, 0.25 is 0.15 and it's again 0.25. After that biplane meshing is defined. It starts from the 0 to 100 nanometer with different spacing. After that the region is defined with the material. The first region having the material aluminum gallium nitride with the composition 0.3 and their positional parameter. Region number 2 having nitride material as an insulator with their positional parameter. Region number 3 is gallium nitride as a substrate with their positional parameter. Next, I have defined the electrode statement. Electrode number 1 for source with their positional parameter. Electrode number 2 for drain with their positional parameter. Electrode number 3 for gate terminal with their positional parameter. Electrode number 4 is for the substrate. Next, I have defined the contact statement. The gate work function is 5 electron volt. Source and drain work function is 3.93 electron volt. Next, I have defined the modal statement, mobility statement. Modal statement. Modal is used in the simulation of HEMT, print and SRH. Next, I have defined the mobility model. The mobility model is the ALBCHIT, ALBREEST model. You can choose this model. You can choose to low field mobility model by specifying the command ALBRCT in the modal statement. You can see that I have defined the command ALBRCT. This is the ALBRCT model. ALBR, the ALBRCT model ALBRCT.N or ALBRCT.P or both on the mobility statement for separate control over electron and hole. I need this model for the electron control, so that I am using ALBRCT.N model in the mobility statement. Next model statement is polarization. In some material system such as gallium nitride and indium gallium nitride, the built-in fields due to polarization and strain, that is piezoelectric effect, can play significant role in the drain characteristics. Atlas introduces these polarization fields as sheet charge at the top and the bottom edge of the region. This will only include spontaneous polarization. If you want to also include the piezoelectric polarization, you can also specify the calculation dot train parameter in the model statement. I have mentioned that you can see that calculation dot train parameter in the model statement. If you specify this calculation dot strain parameter in the model statement, the simulator will automatically calculate strain from the latest mismatch and will calculate the piezoelectric polarization and apply it to the particular region. You can also specify the value of the strain parameter, which specify the axial strain in the region. With strain and polarization set, the simulator will apply a piezoelectric polarization calculated using the strain value assigned by the strain parameter, that is the polar dot scale 0.8. After that, the output conduction band balancement command is used to calculate different parameters such as valence energy band, potential, electric field, electron density, etc. After that, method statement is used. Newton trap and the value of the maximum trap is 20. It will divide the drain voltage 1 to 20 to 20 times. This means the drain voltage is varying from 0.05 to 1 volt. This is the solve initial statement. After this, I have saved the structure file, and the V drain voltage is 1 volt. By using the maximum trap, it will divide it by 20 times. Next is the solve statement, in which I have mentioned the gate voltage. The final voltage is minus 10 volt, and the step size is 0.5 volt. After that, I have saved this low file, and the gate voltage is vary from 0 to 1 volt, and the step size is 0.5 volt. After the initial solution is obtained from it, the gate voltage is ramped to 0 to minus 10 volt. Then the ID VGS characteristics is extracted from minus 10 to 1 volt at VDS 1 volt. After that, a family of drain current characteristics are then simulated with and without lattice heating taken into count by ramping the drain voltage from 0 to 15 volt at various gate voltage minus 3, minus 2, minus 1 and 0 volt. After the initial command, the gate voltage is minus 3 volt, in which the drain voltage is vary from the 0 to 15 volt at the increment of V increment 0.05 volt. Another is a gate voltage is minus 2 volt, in which the drain voltage is vary from V start, that is 0 volt, to the V stop at 15 volt. At the increment of V increment is 0.05 volt. 0.5 volt. I have run this program for the various VGS voltage. These four curves are obtained without using the lattice heating model. After that, the same procedure is adopted for the lattice heating model. Start with same wireless command. In the mesh region, I called the previous simulated structure, that is gallium nitride FET GaN FET EX03_0 structure. Contact malfunction of gate, source and drain are same. In the model statement, one extra temperature model is included, that is lattice temperature. Next is the drawing command. This one is for the thermal contact command with the positional parameter with external temperature is 300 Kelvin. After that, this output command and the method statement. After the initial solution is obtained, ID VDS curve is calculated at various gate to source voltage minus 3, minus 2, minus 1 and 0 volt, in which the drain voltage is varying from 0 to 15 volt with step size 0.5 volt. But the difference is that this time the drain output characteristics are then simulated with lattice heating model. At last, the Tonyplot command is used to extract the log and the structure file. When you run this program, you will get 3 log file and the 1 structure file. This is the structure file. This is the aluminum gallium nitride material. This is the backside is the Si3NO4 insulating layer, and this is the aluminum gallium nitride layer that is connect the source and the drain region. This is the first log file. First log file is plotted between ID versus VGS curve at VDS 1 volt. Drain to source voltage is 1 volt, in which the gate voltage is varying from minus 10 volt to 1 volt. This is the low curve. The off current is approximately 10 raised to power minus 15 and the on current is very high, 10 raised to power minus 1. Second curve is the ID versus VDS curve. At the gate to source voltage is minus 3 volt to 0 volt, in which the drain to source voltage is varying from 0 to 15 volt. This is the curve obtained without including the lattice temperature model in the model statement. This is the last third one, the log file, in which the curve is plotted between ID versus VDS at VGS voltage is varying from minus 3 to 0 volt. the VDS voltage in the graph is varying from 0 to 15 volt. This is the graph obtained with including the latest temperature model in the model state. My dear friend, this is end for today. Share my channel as much as you can.